Welcome back to the fifth session of RDGG. May I request Professor Ampal Vijay Kumar to officially welcome the gathering.
Welcome to all of you, and I'm happy to invite Professor Arvind, the Institute of Mathematical Sciences, Chennai, to introduce the speaker. Over to Arvind.
Thank you. Welcome everyone. I'm very happy to introduce Mr. Saul Friedman, today's speaker. I'm just looking at his bio, which was sent to me by Vijay. He's a Bachelor of Engineering in Electrical and Electronics, as well as a Bachelor of Science in Mathematics and Physics from the University of Western Australia. A dual degree, as we would call it in India. It's very impressive. And honors in mathematics and statistics in the following year, and then a Master of Philosophy by research in mathematics, again from University of Western Australia. And now he is doing his PhD at the University of St. Andrews, possibly a student of Peter Cameron.
Yes, that's right.
Okay.
And of Culver-Ronnie Dougal.
Oh, okay. So it's very nice to have you as a speaker with us. The title of the talk is Non-commuting, Non-generating Graphs and Intersection Graphs of Groups. Over to you. So.
Thank you. And thank you to all the organizers for inviting me to talk about my research. So yes, I'll be talking about two different kinds of graphs in this talk. The second graph I'll mostly be talking about towards the end of the talk. And so some of the results in this talk are joined with my supervisors, my PhD supervisors, and I'll mention which ones those are when we get to them. And if at any point in the talk anyone thinks I'm going too fast, please interrupt me and tell me to slow down. So let's begin. So as some motivation, recall that in Peter Cameron's first talk in the seminar series, he defined this hierarchy of groups, or of graphs rather, defined on groups. So in each of these graphs, the vertex set is the set of elements of a group. And Peter pointed out that it's interesting to study the difference between consecutive graphs in this hierarchy. Now, if you weren't at Peter's talk, or if you forgot the definitions of these graphs, don't worry. We're just going to be focusing on the differences related to these last three graphs colored in blue. And note that when we take the difference between consecutive graphs, sometimes we'll remove some vertices from the vertex set, and I'll explain what I mean shortly. So first of all, this final difference between the complete graph and the non-generating graph, that's just the generating graph, and this is of course very well studied. And in this talk, we'll focus on the next difference between the non-generating graph and the commuting graph. So let's define these graphs precisely. So in this talk, G would denote a group. In general, it could be finite or infinite. So the generating graph of G is the graph whose vertices are the non-identity elements of G. This symbol here means set minus, so G minus the identity. And two vertices are joined if and only if they form a generating pair for the group. Now, the graph that we're interested in is the non-commuting, non-generating graph. We denote this by gamma of G. This graph has vertices, the non-central elements of G, and two vertices are joined if and only if they do not commute and they do not generate G. So in other words, they generate a proper subgroup of G. So I'll note that for the generating graph, we remove the identity vertex from the vertex set because, at least for a non-cyclic group, this will never be part of a generating pair, and so it will always be an isolated vertex, so we just remove it. And similarly, for gamma of G, we remove the central elements from the vertex set because those will always commute with every other element, and so they will never be joined to anything else. Now note that throughout this talk, I'll often be comparing the generating graph and gamma of G, and so to make it clear when I'm talking about the generating graph, I'll be using this pink color for the associated blocks, and otherwise I'll just be using this purple color. Okay, so now let's move on to a simple example. So let's consider the group, we'll let G be the group, the dihedral group of order 12, generated by an element A of order 6 and an involution B. So here's one way of constructing the non-commuting, non-generating graph of G. So first, we start with the generating graph. So here, for example, A and B are joined because they generate G, while A and A to the fifth are not joined because they generate a proper cyclic subgroup of G. A cubed is not joined to any other element because A cubed is central in G, and it also turns out that A squared and A to the fourth are also isolated. So now we want to turn this generating graph into the non-generating graph, so of course we just take its complement. So now A cubed is joined to every other vertex, but I haven't drawn in all the edges because that would be messy. And so we have the non-generating graph. We want to take the difference between the non-generating graph and the commuting graph. So we remove all the edges between vertices that commute. So we'll remove these dashed edges and get this graph. And finally, to get gamma of G, we want to remove vertices corresponding to central elements. So we remove A cubed. And so this is gamma of G. So we notice that there are still two isolated vertices. And apart from these isolated vertices, there's a single connected component of diameter 2. And indeed, connectedness and diameter are the properties that I'll be focusing on in this talk. Well, as a motivation, I'll say that perhaps one of the most famous results in the area of graphs defined on groups is this theorem of Brionic and Cantor. So they proved that the generating graph of any non-abelian finite simple group is always connected with diameter 2. And in fact, this result was generalized quite recently by Veronic and Harper. They showed that the generating graph of a finite group has no, if the generating graph of any finite group has no isolated vertices, then it is connected with diameter at most 2. So these are very nice results. And so this naturally leads to the question, what can we say in the case of gamma of G? So in particular, when is gamma of G connected? And whether or not it is connected, what are the diameters of its connected components? So I'll note that gamma of G is a naturally defined proper subgraph of the complement of the generating graph. And since the generating graph often has a very small diameter, you may expect that gamma of G must have a very large diameter. Well, actually, we'll see that the diameter of gamma of G in general is quite small, and it's often as small as possible. But for now, we can make some easy observations. So first, because the vertices of the graph are the non-central elements of G, it's clear that the graph is empty. In other words, it has no vertices, if and only if G is abelian. It's also easy to show that no connected component of the graph can have diameter 1. And so to prove this, I'll make some space by hiding these pink blocks. So let's suppose for a contradiction that there is a component of diameter 1, then there must be at least two vertices in the component, say x and y, and they must be joined by an edge because the component has diameter 1. Now, let's assume, first of all, that x has order at least 3, so that x is not equal to x inverse. Then because y is joined to x in the graph, it's easy to show that y must also be joined to x inverse. However, x and x inverse commute, so they can't be joined in the non-commuting, non-generating graph. And so actually, this second edge can't exist. X inverse can't be a distinct element. Well, that's because, of course, in this connected component, any two vertices must be joined directly, but x and x inverse can't be joined, so this edge doesn't exist. And so x inverse must actually be equal to x, and so x must have order 2. And in fact, this is true for every vertex in this component by the same argument. Now, because x and y are joined, it's also easy to show that each of x and y must be joined to x times y. Now, because x, y, and x times y all have order 2, it's easy to show now that x and y actually don't commute. Well, they do commute, rather. And so because x and y commute, this means that this edge here that we first assumed existed actually doesn't exist, which is, of course, a contradiction. So indeed, a component of diameter 1 cannot occur. Okay, so I just mentioned that the graph has no vertices if and only if G is abelian. Well, what about if there are vertices but no edges? So let's suppose that G is not abelian, so that there are vertices. Now, note that an edge in the graph corresponds to a pair of non-generating elements that do not commute. And so the graph will have no edges if and only if any two, well, whenever we have a non-generating pair of elements, those two elements must commute. And because a non-generating pair of elements corresponds to, well, that means that those two elements lie in a proper subgroup of G. This means that the graph has no edges if and only if every proper subgroup of G is abelian. And a group with this property that is non-abelian but every proper subgroup is abelian, this group is called minimal non-abelian. So Peter Cameron mentioned these groups briefly in his talk earlier in the seminar series, but I'd like to say a bit more about these groups. So as Peter mentioned, in the finite case, the finite minimal non-abelian groups were classified by Miller and Moreno in 1903. In particular, any such group is either a P group or a non-nilpotent group whose order is divisible by 2 primes. Now, in the infinite case, not every minimal non-abelian group is known, but there are some well-known examples, namely the Tarski monsters. These are infinite simple groups where the order of every proper non-trivial subgroup is a fixed prime P. And in fact, Olshansky showed in 1982 that a Tarski monster does exist for each prime P that is greater than 10 to the power of 75. So indeed, these Tarski monsters exist, and they are examples of infinite simple groups where there are vertices but no edges. And there are, of course, also these finite examples, and in each of these finite examples is in fact soluble. Okay, so now I want to say something about the minimal size of a generating set for the group. So let's let D be the size, or the minimum size, of a generating set. So it's quite easy to see that for the generating graph, the graph is only interesting when D is 2. That's because when D is 1, of course, the group is cyclic, and so we know exactly what the graph looks like. And if D is greater than 2, then there are no generating pairs, and so the graph has no edges. Well, in fact, the case D equals 2 is also the only interesting case for gamma of G. So why is this? Well, when D is 1, again, the group is cyclic and therefore abelian, and so the graph has no vertices. On the other hand, if D is at least 3, then again, G has no generating pairs, and so this means that any 2 vertices in the graph are joined by an edge, if and only if they do not commute. And so gamma of G in this case is exactly the non-commuting graph of G, which has vertices, the non-central elements. Now, why is this case not interesting? Well, Abdullahi, Akbari, and Mahmani showed in 2006 that for any non-abelian group G, the non-commuting graph of G is connected with diameter 2. So for example, here's the non-commuting graph of D12, and we can check easily that this is connected with diameter 2. But why is this result true in general? Well, Peter Cameron gave essentially the proof of this result in his talk, but I'd like to give it again because it's a nice short proof that gets us in the right frame of mind for thinking about these graphs. So let's let X and Y be vertices in the graph. In other words, X and Y are non-central elements in G. Then because they're not central, well, then the centralizer of X in G and the centralizer of Y in G must each be proper subgroups of G. And it's not hard to show that the union of 2 proper subgroups of G must be a proper subset of G, which means that there exists an element H in G depending on X and Y that doesn't lie in either centralizer, and so H does not centralize X or Y, which means that X, H, Y is a path in the graph. So we've shown that given any 2 vertices in the graph, there's a path of length at most 2 joining them. And so the graph is connected with diameter at most 2. We can in fact show that the graph is not connected with diameter 1 for the same reason as in the case of gamma of G, and so indeed the diameter is equal to 2. So this is why we're only interested in gamma of G when G is 2 generated and non-abelian. 2 generated meaning that there exist generating pairs. This is because if G is abelian, there are no vertices, and if G is not 2 generated, then we know that gamma of G is always equal to this non-commuting graph, which has diameter 2. Okay, so previously, while we're looking at this non-commuting graph, I want to talk about a related fundamental result about gamma of G related to Maxwell subgroups. So let's let H be a Maxwell subgroup of G. So observe that any 2 elements of H generate a subgroup of H, which is proper in G. And so no 2 elements in H generate all of G. So this means that in gamma of G, 2 elements of H will be joined in the graph directly, if and only if they do not commute. And so it follows immediately that the subgraph of gamma of G induced by the non-central elements of H is exactly the non-commuting graph of H, which has diameter 2. And so this means whenever we have 2 vertices in gamma of G that are non-central elements of a Maxwell subgroup H, we know there's a path of length at most 2 in gamma of G joining those 2 elements. So this is a very useful result when looking at the diameter of gamma of G. And note that this, of course, holds for any proper subgroup of G, not just maximal subgroups, but it's most useful to consider maximal subgroups because this allows us to consider as many elements at one time as possible. Okay, so now we previously looked at the case where the graph has no edges, in other words, where every vertex is isolated, but in fact we can say something more general about isolated vertices. So we'll again assume that G is non-abelian and 2 generated. Now note that a vertex X in the graph will be isolated if and only if, whenever it's part of a non-generating pair, well, the other element in that pair must commute with X. And this corresponds to, well, any non-generating pair of elements is exactly, well, non-generating pairs of elements are exactly pairs of elements that lie in a given maximal subgroup. And so this, what I just said, is equivalent, or rather I'll say that a vertex is isolated if and only if each maximal subgroup containing that vertex also centralizes that vertex. Okay, now it's easy to show that a non-central element X of G is centralized by at most one maximal subgroup. And so it follows from what I just said that X is isolated in the graph if and only if X lies in a unique maximal subgroup M of G and X is central in M. So to explain this a bit, well, if both 1 and 2 hold, then it's clear that this thing over here holds, and so X is isolated. If 1 holds but 2 does not, then X is not central in M, and so of course X is not isolated. And if 1 does not hold, then X lies in at least 2 maximal subgroups. It's central in at most 1, and so it's non-central in at least 1, and so again X is not isolated. So a question that I'm very interested in related to all this is the following. If the vertex X is isolated, can this maximal subgroup M be non-abelian? I do not know the answer to this question in general, and I certainly don't know any examples where M is non-abelian. But what I can say is that if M is a normal subgroup of G, then M cannot be non-abelian. It must be abelian. So why is this? Well, let's assume that X is isolated. Then X lies in this unique maximal subgroup M, which means that for any element Y that doesn't lie in M, X and Y form a generating pair for G. Now, because X lies in the center of M, this means that the center of M generates G together with Y. And because the center of M generates G together with one other element, that means that the quotient of G by the center of M is cyclic. And this quotient is well defined because the center of M is normal, because M is normal. And because this quotient is cyclic, so is the quotient of M by its center. And whenever we have a group whose central quotient is cyclic, well, that group must be abelian, and so M is in fact abelian as required. So we will revisit this general question later in the talk, but for now, just remember that when M is normal in G and X is isolated in this normal maximal, so when we have an, sorry, let me say that again. What you should remember is that if we have an isolated vertex X and it lies in a normal maximal subgroup M, then M must be abelian. Okay, so now we'll move on to the main part of the talk, where I will present results about gamma of G related to certain families of groups. And in the first case, we'll consider groups that have every maximal subgroup normal. So in the finite case, a group with every maximal subgroup normal, well, that's exactly saying that the group is nilpotent. And of course, every infinite nilpotent group has every maximal subgroup normal. But there are non-nilpotent infinite groups that still have every maximal subgroup normal. So this
Saul,
property is...
Excuse me?
Yes?
Saul, your presentation is not visible.
I'm just talking. This is all that's meant to be on the slide.
Fine. Thank you. Sorry.
That's okay. Yeah, so what I'm just saying is that this property, all these groups include all nilpotent groups, but there are some infinite nilpotent groups, there are some infinite groups that have every maximal subgroup normal, but are not nilpotent. And so this property is a bit more general than nilpotency. Okay, so for convenience, we're going to write delta of G to be the graph obtained from gamma of G by removing all isolated vertices. So for example, we've seen the graph gamma of D12 here on the left. If we remove the 2 isolated vertices, we get delta of D12 on the right. Now D12 does not have every maximal subgroup normal, but this is just a nice small example that we've seen already. So I'll now state the main theorem in this case. So this is joint work with my PhD supervisors, Peter Cameron and Corvo Roney-Dougal. So again, we'll let G be a group with every maximal subgroup normal. Then delta of G could be empty, which means that every vertex in gamma of G is isolated, if there indeed is vertex. So that means that either G is abelian or minimal non-abelian. But if delta of G is not empty, then it's connected with diameter 2 or 3. And in fact, if delta of G is connected with diameter 3, then it's equal to gamma of G, which means that gamma of G itself is connected with diameter 3, and in particular, there are no isolated vertices. So if there are isolated vertices, then either every vertex is isolated, or there's a single component of diameter 2. And so indeed, we see here that in all of these cases, the diameter of delta of G at least is very small. And indeed, there are cases where gamma of G itself is connected with diameter 2, which are the cases where the diameter is indeed as small as possible. So I'll say a bit about the proof of this theorem, and to do so, I'll hide the stuff at the top of the slide. So the key result used in the proof of this theorem is as follows. So for an arbitrary group H, we'll let K and L be normal maximal subgroups of H. And we'll also let X and Y be non-central elements of K and L respectively. Then we can show that the distance in the graph between the vertices X and Y is at most 3. So this symbol here, D, means the distance between X and Y in the graph. And in fact, if both the center of K and the center of L are contained in the center of H, then this distance is in fact at most 2. So I won't prove this lemma here, but it involves arguments similar to the fact that the subgraph induced on a maximal subgroup's non-central elements is the non-commuting graph of that maximal subgroup, and similar arguments. Okay, so this lemma actually automatically gives us the first statement of the theorem. Why is that? Well, of course, we've assumed that every maximal subgroup of G is normal, so this result applies to every maximal subgroup. And we know that when we have a non-isolated vertex in the graph, it is a non-central element of some maximal subgroup. So this is just telling us about non-isolated vertices in the graph. And so this tells us that any two non-isolated vertices are joined with a path of length at most 3. And so the diameter is at most 3. We also know that the diameter cannot be 1, so indeed the diameter of delta of G is either 2 or 3. Now what about the second statement in the theorem? Well, let's prove the contrapositive, or rather I'll give a sketch of the proof. So we'll assume that delta of G is not equal to gamma of G, and we want to prove that delta of G then is not connected with diameter 3. So that's the contrapositive of this final statement. So we may as well assume that delta of G is not empty, because otherwise we're done. And so then, because delta of G and gamma of G are not equal, this means that gamma of G has an isolated vertex X. And recall, this means that X lies in a unique maximal subgroup M of G, and X is central in M. And because this maximal subgroup M is normal in G, this means that M is abelian. Now I won't prove this here, but it's not too hard to show that because G has an abelian maximal subgroup, and because every maximal subgroup of G is normal, then every non-abelian maximal subgroup of G has a center contained in the center of G. And so this means that the final part of this lemma above applies, and so actually the distance between any two non-isolated vertices is at most 2, and so the diameter of delta of G is 2, which is not equal to 3, and so we are done proving this contrapositive. Okay, so as I mentioned, this family of groups includes all the finite nilpotent groups, and in fact, in the case of a finite nilpotent group, we can give a more precise theorem than this one. So what I'll say is that a finite nilpotent group, G, is the direct product of its C-level subgroups. And so using this fact, we can derive a more precise relationship between the structures of G and the graph. It's a bit too technical for me to describe here in this talk, so I won't do so. But the proof of this result also uses some more general results about direct products of groups. So I'll talk about those results here. So this is again joint work with my supervisors. So we're going to let A and B be arbitrary groups with A non-abelian. In the first case, if B is not cyclic, then the graph of the direct product of A and B is always connected with diameter 2. On the other hand, if B is cyclic, and if the graph of A is connected with diameter k, then the graph of the direct product is also connected with diameter at most k. So I won't prove this, but I'll state that the main idea used in this proof is that if we have two elements, A1 and A2 of A, if they do not generate A, then any two corresponding elements of the direct product will also not generate the direct product. And similarly, if the elements of A do not commute, then the elements of the direct product will not commute. And of course, this also holds if we replace the elements of A with elements of B. And so basically, it's very easy to have two elements or two vertices in the graph of the direct product joined directly, which is why, especially in case 1, the diameter is always as small as possible. So just some examples. These are not nilpotent, but they're nice small examples. The graph of the symmetric group of degree 4 is connected with diameter 3. If we take the graph of the direct product of S4 with a cyclic group of order 2, this is connected with diameter 2. However, if we take the direct product of S4 with a cyclic group of order 3, then the graph has diameter 3. So this at most k part is important because when taking the direct product with a cyclic group, we could either remain at diameter k, or we could go to a diameter that's strictly less than k. And note that all three of these groups are indeed 2 generated. Right, so you'll notice in particular that if we take the graph of a direct product of 2 or more non-abelian simple groups, then the graph will always be connected with diameter 2. This is a very different situation to what happens for the generating graph. And so to discuss this, I'll hide this stuff here to make some space. So in 2013, Crestani and Lucchini proved that for any positive integer k, there exists an odd prime p and a positive integer n, such that excluding isolated vertices, the generating graph of the direct product of n copies of the simple group PSL 2 to the p is connected with diameter greater than k. So again, for the non-commuting non-generating graph, if we take a direct product of non-abelian simple groups, we always have diameter 2. But for the generating graph, excluding isolated vertices, the diameter is unbounded. So these two situations are very different. Okay, and again, using this lemma and some other results, we can deduce more information about the graph of a finite nilpotent group. But for now, I'll move on from finite nilpotent groups to finite soluble groups. So Lucchini proved in 2017 that if G is a 2-generated finite soluble group, then again excluding isolated vertices, the generating graph of G is connected with diameter 2 or 3. And you'll note that this looks a lot like the result we just proved for finite nilpotent groups for gamma of G, where of course in that case we could also have we could have all isolated vertices. But excluding that case, we again see that the graph has diameter 2 or 3. Well, does this theorem still hold for soluble groups in the case of gamma of G? That's the question, and the answer in fact is no. So there exist 2 generated finite soluble groups G. There's a diagram of the Maxwell subgroup structure of such a group G on the left. We have Maxwell subgroups M1, M2 up to Mn. The intersection of any 2 distinct Maxwell subgroups is the center of M1, which properly contains the center of G, and any Maxwell subgroup other than M1 has a center equal to the center of G. Now, whenever a group G satisfies these properties, in fact, the graph of G has 2 connected components, each of diameter 2. So one of the components consists of the vertices that are non-central elements of M1, and the other component is all the remaining vertices. So why are these components disjoint? Well, starting from a vertex in M1, we of course can't join it to a vertex in the center of M1 because these 2 vertices commute. Now, additionally, every vertex outside the center of M1 lies in a unique Maxwell subgroup, because of course the intersection of any 2 Maxwell subgroups is the center. And so we can't join a vertex in M1 outside the center to a vertex outside of M1 because these 2 vertices will generate the full group. So they're not joined. So indeed, these 2 components are disjoint rather. So why is this upper component connected with diameter 2? Well, these vertices are exactly the non-central elements of M1, And recall that the subgraph of gamma of G induced on the non-central elements of a maximal subgroup is exactly the non-commuting graph of that maximal subgroup, which has diameter 2. So this component is just the non-commuting graph of diameter 2. Okay, now what about this lower component? Well, recall that any non-central element of a group is centralized by at most one maximal subgroup. And in fact, because these vertices in the center of M1 are centralized by M1, they can't be centralized by any vertex outside of M1. So that means we can start from a vertex in the center of M1 and go directly to any vertex outside outside M1, and then back to any vertex in the center of M1. Similarly, we can start at any vertex outside of M1, then go directly to any vertex in the center of M1, and then back out again to any other vertex outside of M1. And so indeed, this lower component also has diameter 2. Okay, now we'll call group G a 2-2 group if the graph of G consists of two connected components of diameter 2.
Saul, can I ask a question here?
Yes?
I mean, this existence of such two generated finite soluble groups, it's you actually have examples, a family of examples, or it's
Yes, I'll give examples on the next slide.
Okay, thanks.
That's a good question. Thank you. Yes, so they do exist, these groups, and so this any group satisfying these properties here is a 2-2 group. So we can now state the main theorem about these finite soluble groups. So in the case of a finite soluble group, G could be a 2-2 group, or otherwise we get exactly what could happen for a finite nilpotent group. So basically, if G is not a 2-2 group, then delta of G could be empty, or it could be connected with diameter 2 or 3. And again, if delta of G is connected with diameter 3, then delta of G is equal to gamma of G. Now, in the case of infinite soluble groups, actually the theorem is almost the same, except there may exist a group G where gamma of G is connected with diameter 4. I don't actually know if such a group G exists. If it does, it has to have very specific properties, but I at least haven't been able to rule out that case. So when we have an infinite soluble group, maybe we could have diameter 4, but maybe not. Okay, so I think that these 2-2 groups are interesting. And indeed, to answer the question that was asked, let's take a look and learn a bit more about these 2-2 groups in the finite case. So first we need this theorem of Adnan. So a finite group G has exactly two conjugacy classes of maximal subgroups, if and only if there exist distinct primes P and R, such that G is the semi-direct product of a C-love P subgroup P and a cyclic C-love R subgroup R. And we also need R to act irreducibly on the quotient of P by its Vertini subgroup. Recall that this Vertini subgroup is the intersection of all of P's maximal subgroups, and this quotient is elementary abelian, and so it's essentially a vector space. Okay, so now that we have this theorem, I won't prove this result here, but we can show that a finite group G is a 2-2 group if and only if G is as above. In other words, it has exactly two conjugacy classes of maximal subgroups, and we also need the center of P to be equal to the Vertini subgroup. So now, indeed, let's look at an infinite family of examples of 2-2 groups. So let's consider the simple Suzuki group defined over a field of order Q, where Q is 2 to the power of an odd integer I with I at least 3. And this group is also the twisted group of Lie type of type B2 defined over FQ. So a C-love 2 subgroup of the Suzuki group has a normalizer N equal to the semi-direct product of a group H of order Q squared and a cyclic group of order Q minus 1. Now it turns out there exists a prime divisor R of Q minus 1 such that the subgroup of N equal to the semi-direct product of H by the cyclic group of order R is a 2-2 group. So I won't prove this fact here, but it is a fact that these are all 2-2 groups. So this gives examples of 2-2 groups when for each odd integer I. So you'll note that each of these examples of 2-2 groups has even order, and in each case the cyclic R subgroup actually has prime order R. There are also examples of 2-2 groups of odd order, and also examples of 2-2 groups where this cyclic R group does not have prime order, so it has order a power of R. And in fact, the smallest 2-2 group has order 96. Okay, so that's all that yes?
In this theorem of Adnan, What will the two conjugacy classes actually look like?
Well, one of the conjugacy classes has to be a normal maximal subgroup. So that just consists of one. And then, all right, so let me try to remember. Yeah, so if you let Q be the unique maximal subgroup of R, then one of the maximal subgroups will be the semi-direct product of P and Q.
I see.
And the other one, I think, will be the group generated by 5P and R, something like that.
I see. Okay.
Yeah, and the second maximal subgroup I mentioned was normal, and the first one is not normal, but the conjugates of those form the conjugacy class.
Okay.
I think that's correct, anyway.
So this condition ZP equals 5P, it's almost like the extra special situation, right?
Yes,
I mean,
it
there's
is.
P dash missing, that's it. But
Yeah.
I mean, that doesn't mean anything, right? In this case, so
I don't think so. It's quite possible that it does, and I just haven't realized it. But I don't think it's as easy as saying that it's extra special or something like that.
Okay.
Yes, I think actually it's special because you've got something acting irreducibly modulo phi, and phi is contained in the derived group. Sorry, do I mean that? No, phi contains the derived group. I beg your pardon. No, I take.
Yeah. Well. So of course, any special group satisfies this property, but for extra special groups, you also need the order of the center to be equal to P. But yeah, this is almost like a special group. Yes. All right. So good questions. Thank you. So now let's move on from. So actually, I should mention also that because all these groups here are divisible by 2 primes, this means that any finite 2-2 group is soluble. So now let's move on to insoluble groups. And this time I will really only talk about finite groups. So there are 3 cases I want to look at. In the first case, if the quotient of G by its center has a proper non-cyclic quotient, then the graph of G, gamma of G itself, is connected with diameter 2 or 3. In the second case, if G has trivial center and G is not simple, then delta of G at least is connected with diameter 2 or 3. And if G is simple, then delta of G is connected with diameter at most 5. Now I'll note that I don't know if there is an example of a simple group G where delta of G has diameter 5. There are examples where the diameter is 2, 3, and 4, but I don't know if 5 can occur. But I want to say, well, where does this value of 5 come from? So let's assume that we have 2 maximal subgroups M1 and M2 of the simple group G, and we'll assume that M1 and M2 have even order. We'll let X be a non-central element of M1, Y a non-central element of M2. And because M1 and M2 have even order, there of course exist involutions, A in M1 and B in M2. We can in fact choose A and B, such that A is not central in M1, B is not central in M2, and A and B do not commute. Now because A and B each have order 2, they generate a dihedral subgroup, which is of course proper in G, because G is not dihedral. And this will be important later. Note that this dihedral subgroup intersects non-trivially with each of M1 and M2. Now, because A and B don't commute, and they don't generate all of G, they're joined in the graph. Also, X and A are non-central in M1, and so we know that the non-central elements of M1 in gamma of G correspond to the non-commuting graph of M1, and so there's a path of length at most 2, joining X to A, and similarly, joining B to Y. So there's a path of length at most 5, joining X to Y. So this holds whenever we have 2 maximal subgroups of even order. And so basically, it only remains to consider the simple groups G that contain maximal subgroups of odd order. And so these groups have been classified, and so all we have to do is look at these cases where there is a maximal subgroup of odd order to prove this result. I won't go into further details here, but we can do that to prove this. Now you may have noticed that actually not every insoluble group has been accounted for here, because for example, in cases 2 and 3, we could have central extensions of these groups that aren't covered in case 1. So let's let H be a central extension of G. It turns out that if G has trivial center And if the graph of G is connected with diameter k, then the graph of H is also connected with diameter at most k. So the question then becomes, is there a finite insoluble group G where delta of G is not equal to gamma of G? Because we know that delta of G is always connected, but we don't know at this stage if gamma of G is connected. So I don't know the answer to this question. I at least don't know of an example where these are not equal. But note that if these are not equal, then that means exactly that gamma of G has an isolated vertex. So that brings us back to the question of isolated vertices. So recall, a vertex of the graph is isolated if and only if X lies in a unique Maxwell subgroup M of G and X is central in M. And recall the question.
I have a question, sorry.
Yes, yes.
If G is simple, we know that there are probably many pairs of elements. Random pair of element, would it be a generating pair for G?
Yes, yes.
So it means G complement and the delta G complement.
Yes. So it is quite surprising, even though there are lots of generating pairs for a simple group. In many cases, the complement, in fact, a proper subgraph of that complement, also has quite small diameter. Yeah.
Is there any intuitive reason why that? I mean, why that's the case? Or can we say something about the degree of delta G, the maximum degree?
I haven't thought about that at all, but that is a very interesting question. But I haven't thought about that at all.
Okay.
Thanks for the question.
Thank you.
Yeah, so the question is, if X is isolated, can this Maxwell subgroup M be non-abelian? So again, I don't know the answer to this question, but an important fact here is that no finite insoluble group contains an abelian Maxwell subgroup. So if the answer to this question is no, at least in the finite case, then that means that no finite insoluble group has a graph with an isolated vertex. And so in this case, indeed, if the answer is no, then every finite insoluble group G has delta of G equal to gamma of G, which means that gamma of G itself is connected with diameter at most 5. So again, I would be very interested to know the answer to this question, but at least for now, I do not know the answer. But now let's move on to the second graph that I wanted to look at, the intersection graph of a finite simple group. So this was defined by Ciccone and Pollock in 1969. We denote this graph by sigma of G, and this graph has vertices, the proper non-trivial subgroups of G, with two vertices joined if and only if they intersect non-trivially. Now this graph is actually related to gamma of G, or more precisely to the non-generating graph of G, because if the subgroups H and K intersect non-trivially, then any element in this intersection will be joined directly to any element in H and any element in K in the non-generating graph. Okay, so in this talk, we'll focus on the case where G is a non-abelian finite simple group. And so certain things are known. So for example, we know that sigma of G is always connected. This was proved by Shen in 2010, and independently in the same year by Herzog, Longobardi, and Mai. In fact, Herzog et al. Were looking at the subgraph of sigma of G induced by the Maxwell subgroups of G, but their results easily imply that the full graph sigma of G is connected. Now, what about the diameter of the graph? Well, first, I'll state that Shasavari and Khosravi proved in 2017 that the diameter of the graph has a lower bound of 3. And there are groups G that achieve this lower bound, so this is best possible. So what about the upper bound? Well, Herzog et al. Proved an upper bound of 64. This was reduced to 28 by Mai in 2016. And I was recently able to show that 5 is the best possible upper bound. So any group, any non-abelian simple group G has, in the finite case that is, has a diameter of at most 5. And the diameter of the intersection graph is equal to 5 only for the baby monster group, that is the second largest sporadic simple group, and also for certain unitary groups PSU and Q, where n is an odd prime. For example, PSU 72. So this right now is the only example of a unitary group that I know of where the diameter is 5. There are also examples of unitary groups where the diameter is 3 or 4. So it's currently an open question to determine which of these groups has diameter 5, or indeed which have 3 and 4. So to prove this result, we again, for reasons I'll explain shortly, we want to look essentially at the groups that have Maxwell subgroups of our order. And so we can do that in each case. For example, in the case of the linear groups, we use a nice argument of Peter Cameron involving the action of the linear group on the set of one-dimensional subspaces of the associated vector space. But in this talk, I'll just focus on the proof related to the baby monster group. So we'll let G be the baby monster group, and we'll show that the graph has a diameter equal to 5. So let's let M1 and M2 be maximal subgroups of G, and we'll assume that S1 is a proper non-trivial subgroup of M1, and S2 is a proper non-trivial subgroup of M2. And let's consider the distance in the graph between S1 and S2. So we want to show that this distance is always at most 5, and that there exist choices of S1 and S2 where the distance is at least 5. And note that we can assume that S1 and S2 are not maximal in G, because, well, M1 contains S1, so any neighbor of S1 in the intersection graph will also be a neighbor of M1. So the distance between M1 and any other vertex will be at most the distance between S1 and that other vertex, and the same for S2 and M2. Okay, so first, let's assume that M1 and M2 have even order. Then, as we saw when considering gamma of G, there's a dihedral subgroup intersecting non-trivially with each of M1 and M2. Note that this tilde here means that S1 is joined to M1 in the graph. So here we have a path S1 to M1 to D to M2 to S2, and so this is a path of length at most 4. So the distance between S1 and S2 is at most 4. So this, of course, applies to any two maximal subgroups of even order in a simple group, a finite simple group that is. And so this is the reason why it's most interesting to look at the case where G has a maximal subgroup of odd order. And indeed, we can assume that S1 lies in no maximal subgroup of odd order, of even order rather. So it only lies in maximal subgroups of odd order. Then it turns out that S1 is a cyclic group of order 47, and the maximal subgroup M1 is the semi-direct product of S1 and a cyclic group H of order 23. Now, there exists a maximal subgroup L of G that contains H with the order of L even and the square of the order of L greater than the order of G. Now, because M1 and L both contain H, M1 and L are joined in the intersection graph. And because the square of the order of L is greater than the order of G, this means that in the set product of L and any conjugate of L, there is at least one element that can be written, well, I guess at least one not identity element that can be written in at least two ways as a product of an element from L and an element from that conjugate of L, which means that these two conjugates intersect non-trivially, and so for every x in G, L is joined to L to the x. Okay, so now if M2 is even order, then because L also has even order, there's again a dihedral subgroup intersecting both non-trivially, and so there's a path from S1 to M1 to L to D to M2 to S2, which is a path of length 5. If M2 has odd order, then actually M2 is conjugate to M1, so it's equal to M1 to the x for some x in G. And well, we know that L and L to the x are joined in the graph, and because M1 and L are joined, M1 to the x, which is M2, is joined to L to the x. So we have a path from S1 to M1 to L to L to the x to M2 to S2, and so this is again a path of length 5. So we've considered every case, and so shown that the diameter is at most 5. So now we want to show that there's a choice of S1 and S2, where the distance is at least 5. So I'll make some space. And so now I won't go into details here, but we can use a counting argument involving the maximal subgroups of G that contain the G conjugates of H to show that there's some element x in G such that the distance in the graph between M1 and M1 to the x is at least 3. Now M1 is the unique neighbor of S1 in the graph, and similarly M1 to the x is the unique neighbor of S1 to the x, and so the distance between S1 and S1 to the x is at least 5. And so the diameter is at most 5, and it's at least 5, so it's exactly equal to 5. And so, in fact, we can use a similar argument to show that the diameter of the intersection graph of PSU 7,2 is equal to 5. Okay, now just briefly, let's return back to gamma of G. And so here we have a table of some simple groups, and on the right we have either the exact value of the diameter of the graph or an upper bound for the diameter. In these first two rows, the diameter was calculated computationally using magma. For the third row, we just saw that the intersection graph of the baby monster and PSU 7,2 has diameter 5. And it's therefore easy to show that because of this, the diameter of gamma of G is at least 4. We can also show that in each case the diameter is at most 4, so indeed it's exactly equal to 4. And using various techniques for these other families of groups, we can prove these other upper bounds. Note, however, that I don't know if any of these upper bounds are tight, it's possible that maybe some or all or none of these upper bounds could be reduced. All right, now I have one more slide in the talk. Do you want me to stop here, or should I go to the final slide and talk through that?
Please go ahead.
Okay, thank you. So I just want to say a bit more about infinite groups, give some examples of the graph of gamma of G for these infinite groups. So first, let's look at Thompson's group F. This is the two-generated group given by this presentation. It's an infinite group, and its commutative subgroup is an infinite simple group. Now, it's well known that this commutative subgroup is the unique minimal normal subgroup of F, and the quotient of F by this subgroup is isomorphic to Z squared. Now, I won't explain how exactly, but we can use these facts to show that the graph of F is connected with diameter 2. Now, our next infinite example is the infinite dihedral group, which is generated by elements A and B, each of order 2, with no relations between A and B. In this case, the graph consists of two isolated vertices, AB and BA, plus a connected component of diameter 2. So basically, the components of this graph are exactly the same as for the dihedral group D12, which is nice. Now, the next example is the free group on two generators, which is again generated by two elements A and B with no relations between them, and we can consider A and B as having infinite order. So in this case, the graph actually has diameter 2, and it's connected. So to generalize these last two examples, we'll consider the group G generated by two elements A and B with no relation between them, with A having order R and B having order S, where R and S are either infinite or positive integers at least 2. Then either G is this infinite dihedral group, or the graph is connected with diameter 2. And note that this group G is the free product of the cyclic group of order R and the cyclic group of order S. Okay, so that is everything that I wanted to talk about. Thank you very much for listening.
Thank you. Questions? So the infinite dihedral group will look like the elements will be all words without consecutive occurrences of A's or B's.
Exactly, yes.
And so there is this huge connected component of diameter 2, which means what is it? What will if I give, if you have two words, what would a path of length 2 look like? Is it possible to?
It's been a while since I proved this result, so I don't remember exactly. But I can check briefly if you want me to.
No, just to get a sense of what, how one would even prove a thing like this. It's because it's non-commuting and non-generating. So.
Yes. So
I think you can say if you take an element which is not a generator of the infinite cyclic subgroup, then it's inverted by the involutions outside, so it doesn't commute with them. So any element apart from the two generators will be joined to all the involutions outside, and then you can get there in 2 steps. So I think that's the answer to the question.
Okay.
If you want it as words, so any power of AB apart from either AB or its inverse will lie in this component, and you can go via either A or B in 2 steps.
Yeah, as far as again, it's been a while since I looked at this, but I think there is like a lot of choice for the paths between the two elements.
Okay. So in general, small diameter ought to mean that there are vertices of very large degree, right? So if G has diameter 5, it means there must be vertices of degree size of G to the power 1 over 5. It can't be less than, the maximum degree must be at least that large. So, and I suppose if there's one such, shouldn't there be many such elements? Everybody in the conjugacy class of that will all have the same degree, right?
Yeah, I think so, yes.
Hi, this is Sandra Kingen. I had a quick question. What is the intuition behind having all these graphs having small diameter, especially diameter 2? And the reason I'm asking is that a colleague and I proved some results for diameter 2 graphs that we thought would be relatively easy to generalize to diameter 3, but we're struggling with that and not able to go from 2 to 3. So that's why I'm asking, like, what's the intuition behind these graphs having a small diameter like 2?
Well, so I don't know if this is a satisfying answer to your question, but like, for example, let me just go to, well, first of all, this non-commuting graph is like a big part of the graph. So for example, whenever we have a proper subgraph, again, a proper subgroup that is, the non-central elements will be connected with diameter 2. So that explains why, at least among those elements in the same Maxwell subgroup, for example, there's a lot of connectivity. Also, if we have, again, normal Maxwell subgroups, this lemma tells us that the distance is very small, in fact, often just 2. And so I guess, so often I find that it's the case that there are just some elementary results about group theory that tell us that the diameter must be small in many cases. But I don't, from a more graph theoretic perspective, I'm not really sure what the intuition is there.
Thank you.
Okay, and thank you for the question.
Hello, Saul. This is Ongshuman. I just want to ask you that, I mean, so you first started with some groups where the vertex set is the elements of the groups. I mean, non-commutative graph, I mean, non-commuting graphs and so on. And then at the end of your lecture, you talked about some groups where the vertex are the subgroups of the group. So my question is that there are some also other types of graphs defined on groups where the set of vertex is the subgroups. So can we also, I mean, do you have any idea about, I mean, whether those graphs can also be helpful to see or to look into the graphs where the set of vertex is elements of the groups?
So these two graphs that I spoke about here are really the only graphs that I've looked at so far. But I mean, I wouldn't be surprised at all if there are more connections between these kinds of graphs. Well, for example, even let me just go back here. So to prove these this connectivity result and these upper bound results, these authors used a connection between this intersection graph and the prime graph, also called the Grade-Book-Kagel graph, I think.
Yes.
So this prime graph, for anyone who doesn't know, is it's related to a group G, and the vertices are the prime divisors of the order of G, with two vertices joined, say two vertices P and Q joined, if and only if G has an element of order P times Q. And so they used this strong connection between this intersection graph and that prime graph. So again, this is another connection between a graph with vertices subgroups and a graph whose vertices, well, they're not the elements of the group, but it's another graph where the vertices are something else entirely. So again, I wouldn't be surprised at all if there are more connections like you suggested.
Can I jump in and say something here?
Of course.
Yes. If you take a group and make a bipartite graph in the following way. You take on one bipartite block, you take the non-identity elements of the group, or perhaps the non-central elements. I don't care too much. On the other side, you take the non-trivial proper subgroups, and you join if the element lies in the subgroup. Right? So that's a bipartite graph. Now, if you take two steps in this bipartite graph, if you take an element, you go to a subgroup, and you go back to another element, those two elements lie in that proper subgroup, so they don't generate. So this gives you the non-generating graph of the group. On the other side, is that okay? Agreed?
Yes.
On the other side, you have the subgroups, and if you take two steps from a subgroup, you go to an element and then to another subgroup. That element lies in the intersection, so those two subgroups are joined in the intersection graph.
Right.
And now it's easy to see that two graphs related in this way, the connected components match up, they're bijective, and two corresponding components have diameters that are either equal or differ by at most 1. Now, this is actually a very nice principle because you can apply it also to commuting elements and abelian subgroups, and you get this relationship between the commuting graph and the intersection graph of abelian subgroups. And also, you can apply it to the enhanced power graph, for those who remember what that is, and on the other side, the intersection graph of the cyclic subgroups. So you get a lot of connections between various types of intersection graph on specific subgroups and graphs defined just on the group.
That's very interesting. So is it possible then to, from the intersection graph, to recover the other side, the non-generating graph? Because all the information ought to be there in the, or maybe not.
It should indeed be there. Now, if you take, you could look at it like this. So if you take the common neighbors of a vertex on one side in the bipartite graph, that's a clique in this distance 2 thing.
Yes.
So what are the maximal cliques in the non-generating graph? Well, they should be the maximal subgroups, except I'm not sure whether they really are. This works very nicely if you look at the intersection graph of abelian subgroups and the commuting graph, because a maximal clique in the commuting graph is a maximal abelian subgroup. So you can certainly recover them in that case.
Okay.
But I think it's a little more difficult in the case of the non-generating graph and the full intersection graph. But there are certainly, there's a question. I like your question. It's a good question that we might want to think about.
Yes. Even in your talk, I didn't follow up on the question that I was really keen on, the realizability question. I'll go back to it soon.
Yes. Okay. Good.
And
good.
I'll write to you about it.
Yes, please do. Please do. Yes, I mean, one of the nice things I like about this seminar is that it generates so many ideas. People write to me and say, well, have you thought about this? And
yes.
So lots of good things happen. And Saul, you may very well find that people come up with interesting questions or ideas on what you've just told us about.
Well, they already have, yes.
Oh, yes, okay. Indeed, yes. Yes, okay. Right. Yes, so, okay, that's all I wanted to say at that point, I think.
Thanks, Peter.
Are there any further questions?
Yeah, hello, Saul. This is Sanjay. I have a question.
Okay.
In the last slide, you discussed about infinite groups. Can you go to 19? Yeah. So here for gamma, if it's connected with diameter 2, all the groups we have considered with 2 generators. So if you take more than 2 generators, so does that evidently follow that the diameter will be, or?
Yeah. So as I mentioned earlier on, if we have so are you asking if like the minimum size of generating set is 3, for example?
Yeah.
So if the so for example, if we take the free group on 3 points, then that's not 2 generated, and so then the graph is just a non-commuting graph, which is diameter 2. So again, the only interesting case is when the group is 2 generated.
Yeah. Oh, yeah. Okay. Fine. Thank you.
Yep, thank you for the question.
More questions?
Can I ask a question?
Yes.
Please go.
Is it possible the condition that for the graph the group must be 2 generator? Yes.
Mm-hmm.
So did you think about that, how we can drop this condition, for example, by joining all the such graphs, running all these graphs on the 2 generator subgroup of the graph, then consider a new graph without the restriction that the graph is interesting only for two generator groups?
That is a very interesting question. I hadn't thought of that, but again, that would be very interesting to look at. Yes.
Okay.
So
Again,
thank you for that.
can I mention something here?
Yes, please.
Andrea Lucchini has defined a kind of graph to get around the question that we're only using two generators. So he defines a graph where you join X and Y if X and Y belong to some minimal generating set for the group, right? And he has proved various things about that. I can't now remember exactly what they are, but I'm sure if you look at some of his preprints, you'll find results about that.
Yeah, so I suppose you could take some kind of complement of that and then take the non-commuting elements from that to define the new graph.
Mm-hmm. Yes.
If there are no further questions, since it is already nearing 5:40, I think we can conclude today's session.
Yes, yes. Thanks, Saul, for a wonderful talk.
Yes.
Thank you all for listening.
Yeah.
Thank you all
Thank you.
for your active participation, and special thanks to today's resource person for his valuable time. The next session, as already informed, will be, just 1 second, I'll share the screen, will be on 5th of May, next Wednesday, and will be handled by Sudeep Bera from IIT Bangalore. So, see you all then. Once again, thank you all.